Good morning, guys. How are you doing? Today it's been a while. Actually, let's just start there. I've been offline for a bit, but I'm back now, and in my time away, discovered a few challenges that my students have. So this year, I've had about three students. They had a similar project. So the problem was common and it has to do with distillation. So distillation itself is not so difficult. But the thing is, when you're doing it on COCO, there are certain things that you need to be aware of and you need to be able to solve from the start. So I took the very same problem, created an hypothetical situation, and changed the numbers a bit. And this is what we're going to be working with now, so that I can show you what the challenges are in COCO and how you can solve them when you're doing your simulations. So let's get started. Let's not waste any more time. I'm glad to be back. I hope my sessions so far that I've posted online have been very helpful. It is the feedback that I get from most of my students who sign up for my assistance. So I will keep doing this, and hopefully it keeps helping someone out there, finish the BTech engineering degree and hopefully move on to greater things in life. So let's get started. So this is the stream that I want to further purify. I'm interested in acrylic acid, and it's at 92%, and I wish to increase its purity, let's just say to 99% or 97, whatever, right? So I'm first gonna try and do this as it is on COCO, so that we can see what happens, if it runs, if it doesn't run, and then we're gonna go through the process together to try and solve the problem. So let's get started. So I've got a pressure of 4.3 atm. We might as well change that to 1 atm. There's no need to put in additional units. That's the temperature coming in. We've got 100 kilomoles per hour, and this is our composition. So we're gonna go to COCO. Those of you who are new to COCO, feel free to call me if you need an introduction to COCO, but I will try and explain everything that I do so that when you do get started with your simulation, you have an idea of where everything is. So the first thing we're going to do now is choose our property model and add our components. So we're going to go to this icon here. It says configure flowsheet. If you go to file, it's not on file. Let's go to flowsheet. There it is again, configure. So you can either find the little icon with the little two Erlenmeyer fast, I hope that's what they are, or you can go to for configure, and when you click that, this screen will pop up. So what you want to do then is you want to go to property packages, and you're going to go add. Once you do that, you're going to choose either the concept, which in certain cases, especially if you know you're going to have to do separation processes, it's better to start with concept all the way from the beginning and run with concept. But most problems are set up in such a way that you are better off running it with TEA. So we are going to run with TEA at first. If I do get time, I will show you what happens when you run with concept property package directly. But if ever you're now having a challenge and you want to check if you can solve your separation column quickly, it's best to start your simulation from concept. But let's go the difficult way around so that we can pick up the problems that I want to highlight today. So we're gonna go TEA, and we're gonna go new property package. So let's call this our distillation tutorial. Description, let's call it troubleshooting. So those who are new to concept, you have to choose a property model. So these are for those who are new to concept or COCO, and those who are new to simulation. So you have to choose a property model. Now, if you go to your design textbook, there's a chapter that deals with simulation specifically. And if you go through that chapter, they will explain to you what a property package is, how it works, how to select it. The basic thing about property packages, it's just like your ideal gas law, where you are doing predictions of your thermodynamic outcomes based on that package on that calculation model. So Peng Robinson, Suave, Roderick Kwong, these are different property packages that were created by different engineers, different scientists. And then we then now say, okay, this system that I'm working with will be better suited for Peng Robinson in order to be able to predict the thermodynamic properties of my process streams. So what am I talking about by thermodynamic properties? I'm talking about your densities, your outlet pressures, your enthalpies, your viscosities, all those things. You then use that property model to estimate, just like you would estimate the volume using PV equals to nRT. You will then be able to do the same thing using a now more complex equation. But then this is something you can go look at in your distillation textbook, or you can, if you want to guess which property model will work best for your system, you can Google thermodynamic property packages, and it should give you a tree, a decision-making tree that allows you to follow a path based on the components you have on your system. So for this one, we're going to go with Peng Robinson. Then we're going to add our components. So let's go back to our component list. We have water, acrylic acid, carbon dioxide, propylene, oxygen, and nitrogen. I hope I remember them, but yeah, we'll go back if we need to. So we've got water. We've got acrylic acid. We've got carbon dioxide. We've got propylene. Propylene. What else have we got? I think we've got oxygen and nitrogen. We've got oxygen. And finally, we have nitrogen. Nitrogen. All right, I'm going to click OK. And you'll see it will ask you to assign property package to the default stream type, and you say yes. You will see the importance of this once we go into the flow sheet. So we're doing a distillation now. We're going to add in our distillation column. So you're going to go to this icon here. If you hover over it, it will tell you it's for inserting a unit operation. Let's go to flow sheet and see if it's there. Yes, insert unit operation. So you can either go through the small icon, or you can go through the flow sheet prompt. Then we're going to go to separators. We're going to go ChemSep column or flash, select. There's our ChemSep model. Then we're going to add the flows coming in. For now, you can just add the flow coming in because we still need to do some additional configuration on the column. So let's click on that. Hold on. Yes, sorry. So let's just see what is wrong there. So you double click, it will open up this section here. You go edit. Let's bring back this little thing here. So here's the first challenge I came across. So if you check here, it says ChemSep simple distillation, 20 stages, SI 101, 325, thermo, it says Cape open. So let's see what happens if we try and run it like that. So I'm going to click OK. As I said, we're doing a sort of troubleshooting exercise. So I'm going to go through all the problems that I faced so that you have an idea of what to look forward to when you do your own simulation. Okay, so we go in. I'm just going to try and solve it from scratch, and then we see what happens. So right here we have, you have all your requirements here. And then the one thing that we would need to do is we would need to do a mass balance over this. But of course, it's a bit difficult to do that because now you have no idea where these guys are going to end up. your permanent gases. So we're gonna try and do it using a trial and error method. I will, however, show you a more robust method, which then basically eliminates these permanent gases and then adds them in later. However, for your distillation course, this is something that you might need to discuss with your lecturer because it's a bit of a cheat. But let's go back to our simulation. So what we then have is this screen pops up. So it will show you that these are the components that you have in the system: operation, equilibrium column, simple distillation. It estimated that you need 20 stages, and then you're gonna come and do your column specs. So let's just say we, at our top specification, let's just estimate that we're gonna have a flow rate, distillate flow rate of maybe, let's see, 0.2 kilomoles per second, or let's use a number that I've already used. So hold on a second. So let's estimate we're gonna have a flow rate of, hold on. Let's estimate we're gonna have a flow rate of 0.2 for now. So 0.2. Yeah, let's work with that for now. I will explain the other spreadsheet once we get to it. But then now we know that our acrylic acid is the heavier, our acrylic is the heavier component. So we're going to have its mole fraction at the bottoms. And we're going to specify that as not point, let's just go 97 for now, right? So we're going to close this, say yes, and then go back to our sim. Yes, it's going to change our icon. Let's not dwell there for now. Then we close that. So now you'll see the icon has changed. So let's make sure that our feed actually goes into the column. And we're going to have our outlet streams. Top product. Now we're going to have bottom product. Okay. Let's see. Right. You'll see that it does not want to run. So there's a problem already. But that's the first problem I came across. Now that is easy to solve, but it still doesn't solve our overall problem, and I will tell you why. So let's double click on that again, go edit. So we'll need to start over because the problem now is, you remember I spoke about when we first opened the icon, there's somewhere where it actually said keep open at the bottom. So let's close that again. Let's start again, add a new column. Here we go. And then now, just gonna double click that again, edit. So now I want you to take note. Here where it says thermal, now I'm gonna change it to ChemSep. I'm gonna say okay. Again, it brings up our concept. So there's a very big difference, and I want you to try this again to see where this difference is. If you now check under your properties, before it only had reactions, now it brings up thermodynamics. This is critical. So the reason why that one was not running is because this little tiny step is missing. So now we're gonna go your key values. Let's estimate that using Raoult's law. We all know what Raoult's law is. So your key values are basically actually go back to your thermodynamics, but it also has to do with what we speak about when we talk about property models. And then your vapor pressure, let's use Antoine. I'm sure you all know Antoine. And then we're gonna go ideal for your enthalpy, right? You'll see that if we click run, it will say input is okay. And then you say yes, and then it'll basically run. It'll basically run. It might have errors, so it has no feed. So we have to go back and fix our feed. So let's do that. So yes, configure. So now we're gonna specify our feed. Double click on feed. We said 180 m, so 1325. 1325. Temperature, I think it's set 28 something degrees. I'm just gonna go confirm now. So that's 24.85. So let's use exactly what it has. 24.85. And then let's put in our compositions. Just gonna move this to my other screen so it's easier for me to just fill in the compositions. Just want to do this as quick as possible so that we don't dwell on this too much, so that I can actually take you to the hack. So water 0,06540, then 0,0654, and then acrylic acid 0.92033, 0.92033, and then carbon dioxide 0.83, and then propylene 0.019, and oxygen 0.73. The rest it should calculate itself, and then in terms of our problem, we're given our flows in kilomoles per hour, and that should come to 100 kilomoles. Now, again, just for the benefit of those who are new on simulations, what it will then do is once you specify your stream temperature, composition, pressure, and flow, it will now be able to give you the other thermodynamic properties of that stream. So for example, you'll be able to check what your phase fractions are at the temperature you are at. As you can see, we've got a bit of vapor and a bit of liquid. You'll be able to see your overall properties. That is your bubble point, your bubble point temperature, your bubble point pressure. You'll also be able to see your dew point and your dew point pressure. You'll also be able to see properties such as your enthalpy, your viscosity. You've got here Gibbs energy, thermal conductivity if you're designing a heat exchanger. So now you are able to see everything about that stream because now you fully defined the stream thermodynamically. So let's go back to our system. So now, as you can see, we're almost there, and then we just need to connect our outlet streams. Top product, and then bottom product. And as you can see, we're now ready to run. So let's run it, see what happens. Okay, so it has solved. And what you then get is you've got 84% acrylic acid at the top, and at the bottoms you have 50 kilomoles per hour, which is mainly acrylic acid at 99%. And then at the top product, you've got another 50 kilomoles per hour, and it's got 84% acrylic acid. So you're still losing quite a lot of acrylic acid. And obviously we cannot have that. So this is a problem that I came across, and I tend to figure out how best can we solve this. And the one thing you also want to notice is obviously most of your water will go up because of the fact that your water is the light key component in this case. So I'm going to use this to our advantage, right? Because one thing you can check is with this first iteration, you can see that your bottoms has negligible amounts of the other components, which are more permanent gases. So the only non-permanent gas there is your propylene, but it's also a gas. It's very light, so it's going to report to your top product. So we're going to take advantage of this fact. And what we're going to do, and this is where I said this is where the cheat comes in. Again, it's a cheat. It's not something that you should do. You should do without permission, especially if you're doing this for your course as a subject. So what I will do is I'm going to play with the incoming stream. So here's my incoming stream. And what I will do is I will split the permanent gases out of the stream so that I'm only left with my water and acrylic acid, because those are the two streams that I'm interested in. Actually, then when I'm purifying, actually I am decreasing the water content, and so that the composition or the composition of your acrylic acid in your stream increases. So we're going to put this into a compound splitter. Now, a compound splitter is not a real unit operation. It probably represents something that would be maybe a holding tank where you would allow your gases to evaporate out of the water, and then of the liquid stream, and then you draw off your liquid stream at the bottom. So that would be something like a decanter. So I think that would need a residence time that will allow your gases to actually bubble out of the liquid and then appear in the vapor, and then you have your liquid being mainly water and acrylic acid. But the point is, I want a stream that only has water and acrylic acid, and another stream that has the permanent gases. So let's just have that going there. Okay, outlet, and then you have your split outlet. Okay, let's go back to the flow sheet. Edit. So we're going to add our compounds. So now we want to remove all the permanent gases. So your split factor will be 1 because you want to remove all of it. Let's do nitrogen, 1. Let's do oxygen, 1. Let's do propylene, 1. Let's do finally. So we've got carbon dioxide, nitrogen, oxygen, so we're done. Acrylic acid should not be here. So let's just confirm what we have there. We have nitrogen, carbon dioxide, nitrogen, oxygen, propylene. Those are the ones that we want to get rid of. Let's just go to our spreadsheet. Yes, it's 1, 2, 3, 4 of them. So we're done here. And what I'll do is I'll run the spreadsheet again. I'll run the simulation again. Let's see if it solves better this time. So as you can see, we've now got 49.2, we've got 86. So it hasn't solved better. So what I want us to do now is I want us to do the mass balance around the distillation column. Now that we only have 2 components, it becomes easier to do the mass balance. So the reason why I wanted to put in the compound splitter is for us to be able to do the mass balance easier. So now we're going to go to the spreadsheet again, and we'll bring it back up. Okay, so I've created a distillation column spreadsheet here. Now let's go back to the simulation and check if our streams are the same. 0.933, and it says 98.57. So I'm going to come here and I'm going to change that to 98.57. Please note, so I've created this spreadsheet basically from the same kind of simulation. Just going to take you through it a bit. So the thing with distillation columns, right, is you need to be able to specify what you want from it. So for example, if I've got a feed that is fully defined, right, I'm happy there. right? If I've got a purity that I want to achieve, right, I can put that into my specification. And if, for example, I say that in my bottoms product, I want to have 99% acrylic acid, that means immediately it then solves for the amount of water, the composition of water that will be in the stream. So for example, down here, as you can see, if I say 0.99, then immediately it means I've only got 10%, no, 1% water in that stream, right? Again, if I then define something like, okay, I don't want to lose more than 3% of acrylic acid in my top product as a second definition. So for now, let's change it so that I can show you what would happen. So let's just say I don't want to lose more than 5% of my acrylic acid in my top product, which goes with the water. If I say 0.05, then it immediately changes and defines your water composition. Now, these are your material balance equations for your distillation columns. The flow coming in will be equals to the flow coming out of the distillate plus the flow coming out at the bottoms. And then this is your overall component balance based on acrylic acid. Now, if you take this, right, then you do use that to calculate your flow of the bottoms. This then comes out like this. So it mainly depends on your composition of your distillate of your bottoms that you want. It depends on the flow that's coming in, and it depends on the composition of your acrylic acid in your distillate. So, for example, let's just say now I say, you know what, now we can tolerate losing 10% of our acrylic acid. So let's change that to 0.1. You will see that our flows change, and I just had to change this here. Our distillate flow is actually equals to hold on. So 0.03. So there's a limit to how much we can go. So our distillate flow is equals to that minus your incoming. So let's just do that so that we have 2,600. Okay. So as you can see, I can play around with the compositions that I want. So for example, how much acrylic acid am I willing to lose in the top product? What is the purity that I want of your acrylic acid? For example, if we only just want 95%, you can change that to 0.95. And what will happen is it will change your distillate flow, it will change your bottoms flow. And then let's just say we said we are willing to lose 5% up here. You'll see that now we can't lose 5%. So you can say that because your system is locked, right? So for example, if I say I want a purity of 95%, only a certain amount of acrylic acid is now available to be lost in the distillate, right? So there will be an upper limit in terms of how much acrylic acid I can lose in the distillate. So let's drop that and see what it says. 0.04, it does allow us, but your distillate flow will now be very little. If you're saying that you're allowing a tolerance of 4% in your distillate, then your distillate flow will be very little, unless, of course, we then increase the purity of your bottoms product. And then, as you'll see, your distillate flow rate will start increasing. So let's put our tolerance at 0.03. So that's 3%. I'm gonna come back here and we're gonna say 3%, right? All right, so now that we've defined this, so we're working with a purity of, let's go back to the 99% as our problem statement. So now that we've defined this, then we basically have defined our flow coming in, our flows coming out, our compositions coming out, and now we are able to do our distillation column. So let's go back to our distillation column again. We're going to re-specify it. So now I'm going to double click on the distillation column again, and I'm going to go edit. So now we're going to use values that we have instead of just doing an estimate, right? Instead of doing a try and error basis, I'm going to say. So here, everything remains the same. I will show you one more thing before we finish off. So with the top specification, now I'm going to use a flow rate of our distillate because we have it. So why not? So our flow rate for distillate is 0.0169. So let's see if it will take it like that. Copy. See. Let me just make sure that it's using the right format. Okay, it has accepted our value. And then for the bottoms, then we're going to use what we want to achieve. So mole fraction of component. We want our acrylic acid to be as pure as possible. So we're going to make it 0.99%. All right. So we've now defined everything in our system. So one more thing I want to do before we run the simulation is I want to go check our makeup theory plot. So if you come up here, you'll see that already it gives you an option to see your Maccabi plot diagram. But let's just first run this part so that it updates everything before we go back to the simulation. I want to finish up before we run out of time. Makeup theory plot. And then now you'll see it will bring up the plot, and you will be able to, let me see, I was trying to zoom at some point, and I was not able to. I'm hoping I can this time. So it says click left and drag. Can you hold on? Yes, I want to. Oh, yes, I see. But how do I undo that? Okay. I don't know how to zoom out, so I'm going to have to do another plot. Hold on. Go back to results, and then the copy. Oh, I do not know how to zoom out. We have a problem. Okay, let's do this. Let me see if I can right click and zoom out. And zoom. Yes. All right. So as you can see, if you remember your Maccabi theory plot, you know you'll be able to count your number of stages. So let's do that. It'll be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And as you know, some plots count your reboiler as a stage. So instead of 16, we're going to use 16 because even if it says 15, 16 is still a good estimate. So this is obviously for your costing, for the sake of your costing. You don't want to have more stages than you want. So your makeup theory plot allows you to be able to use the required number of stages rather than overestimating. So we're going to close that now. Yes. Then we're going to go back to our simulation, and hopefully now it will run better and it will give us a more accurate estimate of our column. So I'm going to run it again. All right, so now on top we have our mass balance is now the same as we had it on our calculations. As you can see, we have a flow of 5.82 kilomoles per hour. This is 0.037 acrylic acid that we're losing to the tops. And then if we look at our product, we now have 92 kilomoles per hour, and we've got 99% purity. Now, I am still working on getting rid of that error sign. I haven't gotten a chance to do that, but you can play around as well. Just read the error sign, change your inputs, change your temperatures, and see where that takes you. But the whole point of this exercise was to show you that there are workarounds to certain challenges that you may have on COCO, and it's just a matter of understanding them and understanding how to solve them. I hope this session was helpful. I hope to meet more people. One of the reasons why I love doing these sessions is they expose my work and my passion for helping students to a whole range of other students, and it becomes one of those perpetual cycles that keeps giving. So thank you very much for listening. I hope this will be helpful, and enjoy your studies. If you're starting out, I wish you all the best. If you're about to finish, congratulations, and I hope you keep going until you get to that point where you are happy and satisfied with all your achievements.